In our definition, the connection was defined by its global action, but actually it turns out to be a local operator in the following sense. So let's say y1 and y2 agree on a neighborhood at P, then the value of these connections of y1 and y2 are gonna agree at P. In the x variable, something stronger a whole. So if x1 and x2 agree not, we don't even need it to agree on a neighborhood of P. We just need them to agree at P. And if that's the case, then these two connections are gonna be the same. So that means that the value of this connection at P only depends on the value of y in a neighborhood of P and the value of x exactly at P. So let's see why that is. Now, by the linearity here, this statement is equivalent to saying that if y1 minus y2 is 0 on a neighborhood of P, then the connection of y1 minus y2 must vanish at P. So replacing y1 minus y2 by y, we change the statement to the following. If y vanishes on a neighborhood of P, then the covariant derivative of y in the direction of x must vanish at P. So let's see why that is. Here we are gonna use the product rule. So let's say y vanishes on this neighborhood U of the point P. Now, let f be a bump function supported in U, right, such that f of P is equal to 1. In particular, this means that f times y is gonna be the constant 0 vector field. Why is that? Because, so here at this point, y is 0, so f times y is 0, and at the point outside of U, well, y is not 0, but f is 0, so the product is 0. So this is 0, so this whole expression is 0. Now let's evaluate both sides at P. Right, so y at P is 0. Right, this is 0 because y vanishes in the neighborhood of P, so this whole expression is 0. So we must have that this is equal to 0. But fp was chosen to be 1, or we can just choose any non-zero number. Thus, we see that then this derivative must be 0. Thus, if y vanishes in a neighborhood of P, then its derivative along x at P is also going to be 0. Similarly, we can show that if x1 and x2 agrees on a neighborhood of P, then these two derivatives agree. But now we want to show a stronger statement. We want to show that if x1 and x2 actually agree at P, then these derivatives agree. And that makes sense, intuitive sense, right? Because we want to define this in such a way that when we take the derivative of y, right, at P, it should not matter what happens at the other vectors. We only want to care what happened at the tangent vector right at P. Now again, by linearity, we can rephrase this statement to say that the statement is now if x vanishes at P, then the derivative of y along x at P is going to be 0. Now, because as from the previous part, we know that this expression depends only on the value on a neighborhood of P, so we can take a coordinate neighborhood of P. And then in that coordinate neighborhood, we can write x in terms of the induced basis. So x will have coefficient xi as follows. Remember, this is Einstein's notation, so this is a summation. But by linearity in the variable x, we can pull out this xi. So we get that this is going to be equal to, at P, this is going to be equal to xip times this. But this xip has to be 0 because x is 0 at P, so all of its coordinates have to be 0 at P. And so this derivative vanishes at P as claimed. Thus, connection is a local operator. And so by this lemma, we can actually write this expression now as differentiating y along a specific tangent vector. Because what happened outside of this tangent vector doesn't determine the value of this. The derivative of y along x at P depends only on the value of xp anyway. So we might as well think of that as the derivative of y along the vector xp instead of the vector field. So this is about connection in general. Next we'll talk about the type of connection we're interested in, the linear connection.